Okay, everybody, welcome back to CSE 373. Today, we're going to be talking about an exciting new ADT called priority queues, and we'll talk about a new data structure called heaps that implements that ADT. Priority queues are one of my favorite ADTs, and their heap implementation is one of the coolest ones, I think. Part of it is because every step of the way is a completely non-obvious turn. And so it's really like a surprise each time. You're like, wow, really? That's how you're going to implement it? So hopefully you find these as cool as I do. And we can see some really cool tricks. In this video, I'm just going to mostly talk about announcements and do a bit of a review from what we saw last time. And in the following videos, I'll explain what this priority queue thing is, what these heaps are. We'll get there. So in terms of some announcements, as a reminder, Project 2 is due on Friday at 11:59 p.m. PDT. As a reminder, just like every other project and exercise, you can use late days. This project is a partner project, so you could submit as a pair. So just wanted to remind you that that's a thing. Again, Project 2 tends to be one of the tougher ones, especially that iterator part, so make sure you're starting that a bit earlier because it's going to be hard to get that fully finished by Friday if you're starting on Friday. I also wanted to say a premature thank you for filling out that mid-quarter feedback. This video is being recorded a bit before I have actually had a chance to sit down and look over the results with the course staff. So we are going to thoroughly look through those responses and decide what feedback we are able to implement and so on. But again, this is being recorded a little bit earlier, so I'm not able to talk about that quite yet, even though this is Wednesday's lecture. So by next time, I will definitely have a story for you about kind of what we saw from that feedback. In terms of what we saw last time, last Friday, we started talking about kind of the real world implications of how computers run. So we talked about this idea of memory and your CPU and how it accesses that. We talked about how RAM is nice, but it can be a little slower, at least from the perspective of the CPU. And so we introduced lots of other concepts here like caching. When you go to an array, when you go to memory and grab one value, you actually grab back many. Because it's trying to optimize for programs that use locality, either spatial or temporal. So we talked about things like linked structures tend to not do really well in this system because there's no guarantee that the nodes are next to each other. And so this is one world implication is usually array structures tend to be slightly faster in terms of low order constants. Remember, our big O analysis is still going to be valid. It talks about how things scale asymptotically. It just tells you the rate of growth. But this kind of real world implication kind of gives you a hint at like what those constant factors might be, and those can sometimes make a difference. So we want you to have this in the back of your head. Now we talked about one really fun data structure that tried to take advantage of the structure of your computer's memory system to optimize for large amounts of data. So when you wanted to make a AVL tree over data that was so large, it would have to go on disk, that really slow, sorry about that notification, that really slow part of your computer. Then we would have to use some kind of other structure that optimized for minimizing disk accesses. And so we talked about this idea of the B plus tree. It's this tree that's extra wide. It's allowed to have more children than just two. And we do this so that each node can maximize an entire disk page. Because each time we grabbed one node, we'd pull back a whole page, just like we would with caching. And that was all wasted space in that link structure when you were only looking for a tiny node and all of the space that was brought back. So our idea was make the node as big as the page and store as much information as possible. And in doing so, we can make our tree shorter if we are able to store enough children references in each internal node. And so there's this kind of weird design where the internal nodes are only kind of directions. They just tell you which node to go to next. All of the real data, the key value pairs, are stored on the leaf nodes. We store the keys in the internal nodes as well to help us know which direction to go, but we're not going to be able to answer what value is associated with this key until we get all the way down to a leaf node. But the intent here is that now this tree is short, and so we can minimize the number of disk accesses. And that's what this data structure is really optimized for. So why are B plus trees so disk friendly? Well, we minimize the height, as I was just talking about. Because we let the branching factor, the number of children, be as large as we possibly could, then we're able to keep that tree as short as possible. And we were saying that the limiting factor for this data structure's runtime is the number of times you actually have to go to disk. So trying to minimize that as much as possible is its goal. All of the relevant information to help you find a node fits in a single page of memory. So if it's in the internal nodes, we design the node to fit exactly in a page of memory, so there's as little wasted space as possible. And that part of that design is putting all the key value pairs on their own leaf node pages, trying to fit as many there as we can. So we're really trying to be efficient here, not waste any space that's going to be brought back. And so we use as much of the page as we can, even though it will make some of our operations more complicated, like figuring out which child to go to. You have to kind of look through that whole internal node and figure out which direction is the right way to go. Or when you get to a leaf node, figuring out which key is there, you have to look through all the keys. Even though those operations are more complex than a single node case where you just say, oh, here's the answer, they end up being more efficient in practice. And the reason is all of the other work we were doing to minimize the number of disk accesses far outweigh the few extra microseconds or nanoseconds you'd spend looping through that array in memory that you might save from having fewer keys in that internal node. So that kind of in-memory computation is free with perspective of a disk operation. And so it's okay that those operations are a little bit more complex. So that's kind of what I wanted to remind us about the context of talking about trees and disk and how memory works. Because we'll see, not too much in today's lecture, but we'll see one motivation for maybe using an array structure instead of a tree structure because of these real world implications of making sure our structure is fast. But we're going to talk about this priority queue thing and these heap structures in our next videos.